Hi and welcome to this Leaving Cert Higher Level Trigonometry video. In this video we're going to be focusing on trigonometric function graphs.
So, talking about angles giving you the same value for sine, cos, and tan, we're going to focus a little bit on trigonometric functions. So what I'm going to show you here, you've kind of seen this idea that as I move P, theta is getting bigger, but that point P will always have the point cos theta, sine theta. Tan of theta will then be the gradient or the slope of OP. So as this turns, we're going to be able to create actual functions for sine, cos, and tan. So let's do sine first. So what we have on the x-axis here on the right will be theta, the size of the angle, and y will then give us our value for sine. So moving through this, we're focusing on sine, which is our y value. So working through it, we get our points here. And what we're finding is we get this lovely shape where it creates a wave that peaks at 1, that goes down to -1, and that takes 360 degrees to rotate fully. So it goes from the start back to itself. It goes through one full rotation. And the thing about this is it can keep going. So it can go for another 360 degrees and another 360 degrees. So we can build this function where theta can get bigger and bigger and bigger. We could extend that to go into negative angles. So no longer are we just focusing on this one rotation, but this can be extended to include however many degrees we would like. We can do a very similar thing for cos. So remember, cos is like our x-axis. So our focus on this is we come down and we come back up. So again, we're getting this lovely rotation happening, which creates this lovely curve on our cos um, on our cos graph here. So it looks kind of similar to our sine graph, but has some distinct differences. The first would be that sine will always start at kind of that middle line, so 0, 0 effectively. Cos of theta is always going to start up at either the minimum point or the maximum point or minimum point, depending um, on our translations of it, but it will never start at the middle. Again, this will take 360 to do the full rotation, and we can extend our theta to keep going. So that graph goes on again, like it will keep dipping and coming up and down and up and down and so on. Now, tan is going to be a little bit different. So that is our slope of OP, so our slope. So if you think about it here, there's my slope. It's getting bigger, bigger, bigger until we get to 90 degrees. Now, what's the slope of a vertical line? So actually the slope of a vertical line is undefined. So we cannot put any point there. Instead we have an asymptote there. So we go and now we're going negative, getting positive, and again we don't have we cannot define the slope at that point there, and we go through again. So we get this kind of very different kind of shape than we've had before, and we have what we call a discontinuous graph because there is a point where there is no value for the graph, so 90 degrees, 270, and multiples of those. So again, that theta could be extended and this pattern could be repeated again and again and again. So just some terminology around our function. So we have the period, so that is the length of time it takes to make one full rotation, and it can easily be measured as peak to peak, but you can measure it in whatever way you like as long as you take a full rotation. So for the basic trigonometric graphs, the period is 2 pi. Now I say basic like the ones we've just seen, and that's before any transformations get applied. So the frequency is 1 over the period, and for basic trigonometric functions, it's given as 1 over 2 pi. We're going to see how that changes slightly as we move into the transformations. And the range of the function, first of all, the amplitude is like its height from center, okay? So the center line to the peak, the amplitude. So therefore, the actual range, so from min to max, that's like twice the amplitude. So when we ask for the range of the function, we give our minimum point and our maximum point. For basic sine and cos graphs, it's -1 to 1. For our tan graphs, because they can take any value, it'll be -infinity to infinity. So here are our graphs, and we have sine, cos, and tan. We have our periods are all 2 pi. We have our range for sine and cos are -1, 1, and for tan is -infinity to +infinity. And we have our asymptotes here as well on tan at 90 and 270. That means that there are no values for tan and 90, tan and 270. And if you want to throw that in your calculator, and what you're going to get out of it is an error. Think of tan like your slope. So basically we're asking what's the slope of a vertical line, and we always say that that is undefined. We were never able to get tan of 90 degrees when we were doing junior cert, because we were dealing with 90-degree, well, we're talking right angle triangles. So if I have a right angle triangle, the other angle couldn't be 90 degrees because then it wouldn't be a triangle anymore. There would be no third angle.
It is more likely, rather than working with those normal or pair in trigonometric functions, we're going to be looking at functions that have some element of a transformation. Now, the transformations will be limited to sine and cosine, so our sinusoidal functions, rather than tan. There's not a huge amount that can be done with the tan function in terms of its graph. There is an example later on in this video where we look at a mock question where it was asked, so you can get a sense of the kind of questions. But for the next few examples, we're going to focus on sine and cosine, and specifically the transformations. Now, to try and make it a little bit easier, I've tried to color code it. Now, this might seem really challenging at first, but actually, once you have your little checklist and you can do this quite quickly, these questions become really nice and straightforward. So we're looking at 3 transformations. We have an A, which is a transformation of the y. So you're adding or subtracting a number. So that will move the function up or down. You have B sine or B cos. So that B in front of it, what that will do, it'll stretch the function up and down. So it will change specifically our amplitude. And then we have a CX, so a coefficient of the angle. What that does in general is it compresses the function. So it makes it rotate much quicker. So let's take a look in more detail. So the first thing we're going to do with these kind of questions is find the midline. So the midline is very important. So where is that midline? So the horizontal line that cuts the graph in half. Once we find this, this gives us our value of A, because this should be the x-axis. So if it is moved up or moved down, that will give us the transformation. The second thing then we'll do after we do the midline is to figure out if it's sine or cosine. Now, for this, learn one and the other is the opposite. So what I would always suggest is that we know that the sine graph starts at the midline, so then cosine doesn't. So you should be able to know quite quickly if it's sine or cosine. So here's our example of a sine graph, and you can see that it's starting. Now, when I say starts, I mean at the y-axis. So the y-axis is what we take as starting, because remember, a function can go on forever. And then for cosine, you can see at this start, it starts up here. It doesn't start at the middle. So the midline would be this one here, and the midline would be this one here. So once you know one of those, you'll be able to identify your graph. So the easiest one, I think, is the sine, that the sine graph starts at the midline. So the next thing we want to figure out is if it's positive or negative. Now, this one's a little bit trickier because there's a few different ways you can learn this, but because if we have sine and cosine, the easiest way is to look at the first section. So if that first section is above the midline, so like there, then that's positive. Here, again, even though it's going down, it's still above the midline, so it's positive. If the first section is below the midline, it will be negative. So again, learn 1, I generally think of the positive as being above the midline. So think of that midline as like our new 0. So anything above that at the start will be positive. So it doesn't matter about going up or down or anything like that. It's just where is that first section. The amplitude then is the difference between the midline or center line and the min or max value. So we looked at the amplitude already. It's kind of from the middle up to the top of the wave or top of or the bottom of the wave, so the minimum point or the maximum point. Whatever that amplitude is, that gives us the value for B. The positive and negative that we just talked about will mean that B is either positive or negative depending on where that first section is. So again, nothing there terribly difficult, it's just a little bit to remember. The trickiest one is our C, and we have 2 ways to figure that out. So the easiest way, and the way that I'd always try first, it just may not always work, is how many rotations. So C is how many times the graph rotates normally or in 360 degrees or 2 pi radians. So if it rotates twice, it's going to be 2x. If it rotates 3 times, it's going to be 3x. So that's quite straightforward. Now the problem is that number may not be a whole number, so we may have to work it out. So this little formula is really, really important, and that is that C is equal to 2 pi or 360, depending on what you're working with, divided by the period. And the period is how long it takes to do a full revolution. So it depends on the question which way we'll approach to get our C. So really be very clear on what period means. Example 1. So we're going to take this graph and see if we can write down its function. So we're going to follow our little checklist. So the first thing we want to do is our midline. So our midline is actually the x-axis here. So it goes up to 3 and down to -3. So it's cut right across the middle at the x-axis. So then we need to figure out, well, is this a sine or a cosine graph? So how we do that? So let me put in this midline here. So here's my midline. So then we go to its start. Now it starts here, not back where the line itself starts. It starts at the y-axis. So is it sine or is it cosine? So the answer is it's sine because it starts at the midline. So it's a sine graph. So A is equal to 0 in this case because it's the x-axis. Next thing is it positive or is it negative? So we look at the first section. So the first section is above the midline, so therefore it is positive. The next thing is the amplitude. So the amplitude is basically the distance between the maximum or minimum, if you prefer, and the midline. So there's my amplitude there, and that equals 3. Okay, and then our final piece is C, so how many rotations, or we can use the idea of the period. Now, so I'll always check to see if I can count rotations. So it goes up, down, and back. There's 1 rotation. And here's 2 rotations. So it rotates twice. So C equals 2. No need for that other formula. If you want the other formula, the period is basically how long it takes for 1 rotation. Oh, I went a bit short there. And in our little picture, that gives us pi. So C, no, I don't know how that changed. So C is equal to 2 pi divided by the period, which is pi, which will give us 2. So it gives us the same answer, but there's less thinking involved in the first one. So here we have y equals 0 plus, because it is positive, the amplitude then is 3. It is a sine graph, and then 2x. So simplifies to 3 sine 2x. So this checklist might be very helpful as you're kind of starting, but soon you'll get these kind of 5 steps in your head. And once you have these 5 steps, you can pull out the function for any graph. It's also helpful for the exam questions where they've asked us to identify which graph is which and so on. So example 2, let's work with a few more graphs. So again, we have that same idea of y equals a plus b, either sine or cosine cx. First step is always our midline, so I'm going to put in that midline into both. So let's work through our little checklist here for each. I'll put up the full checklist. So for my first graph, we start with the midline. So I have my midline. So I have y equals and then my midline, which is 2. Next thing I want to figure out, well, is it a sine or cosine graph? So again, I always start on the y-axis, not where the graph itself starts. Remember, it goes on for forever in both directions. So it starts away from the midline, so it's going to be a cos graph. It's going to be a positive cos graph because the first section here is above the midline. So there's my plus. The amplitude then gives me the coefficient, or my b. My amplitude is this height here, which is 2. And then here, now this one, I'm looking at my C. Can I use how many rotations? And the answer is no, because it actually doesn't go to 2 pi. But I can see if I go down, up, and back to where I started, that gives me my period, which is pi. So to work out C, it's going to be 2 pi divided by pi, which is equal to 2. So that gives me my value for C. So I get 2x, and that's my answer. So then for the next one here, we have y equals. Okay, so my midline is at 2, so that's my starting point. I then need to figure out if it's sine or cosine. It starts, remember, at the y-axis on the midline, so this is sine. The first section is above the midline, so it's plus. The amplitude is 1, so a 1 goes here. And then for C, I'm going to see how many times it rotates in 2 pi. So it goes down and up. It only does one rotation in 2 pi. So I end up at 1x. Now, we would never usually write it like that. So we would generally just write it as sine x like this. We wouldn't include our ones. So I have 2 more graphs. Again, let's have our little checklist. Let's put in our midlines. So my first graph, y equals, okay, my midline is at -1. So just a quick note on the midline. Our midlines have been quite straightforward because they've all been whole numbers. But to get the midline, it's the average of the min and the max. So if you add them together, so -4 plus 2, again, -2, and then divide them by 2, you get your -1. So actually the midline, you can use average to calculate that. And the reason I say it is because as we do more real world examples of these, you'll find that sometimes the numbers are not always very, very nice. Okay, so that's our first thing. Is it sine or is it cosine? Well, I'm starting here, so away from the midline, so it must be a cosine graph. Is it positive or negative? Well, my first section is below the midline, so therefore it must be negative. And next thing is our amplitude. So my amplitude is this height here, which is 3. So it goes, this is a 3. And then see, you've kind of 2 ways you can do this. How far does it rotate in 2 pi? And actually, that's not even a full rotation. It's only a half one. You're probably better off going and finding the period of this function, which is 4 pi. So C is equal to 2 pi divided by the period, which is 4 pi, which is equal to a half, or decimal if you prefer. So this is a half x. And we leave it like that. Bracket around that, it's fine. And our final one then is y equals, okay, so our midline, again, between 1 and -5, you can add them together, you get -4, divide by 2, and you get -2. So if you can't do it by eye, if the numbers are a little bit, you know, you might have decimals, we might not have lovely answers. So it's, remember, the average. So that's -2. Next thing I want to do is it's sine or cosine. It's at the midline, so it's going to be sine. The first section is below the midline, so it is negative. And then I get my amplitude. I'm going to do my amplitude underneath this time just to show you it can be done. Because that midline cuts it in half, it shouldn't matter. So this is 3, so I get -2 -3 sine. And then I am looking for my C. So how many times does it rotate in 2 pi? So there's my 2 pi's. Let's count. 1 rotation, 2 rotations, 3 rotations. So we get 3x, and that's our answer. So they're not as challenging as maybe they might seem. There is that little bit of a checklist. And we're going to look at how we can then apply these to exam questions that are based off graphs. And then we'll look at an example which was more of a section B, so a real world kind of problem, which included one of these functions.
Let's take a look at some exam questions. So first one I'm going to look at is the 2010, it's paper 2, question 5b. So now we have seen trigonometric functions appear paper 1, paper 2. Paper 1 would be the functions paper, paper 2 would be trigonometry. So like they could appear on either, and they have appeared on both. So the graph of 3 functions are shown below, and the scales and the axes are not labelled. These are the 3 functions: cos of 3x, 2 cos of 3x, and 3 cos of 2x. So notice that these are all transformations. So some of them have a coefficient, so a constant in front, and they all have a change to how quickly they're moving. Now, what you should be able to pick out straight away is the range of all of these. So this one, because it's cos, it's going to go minus 1, 1. Here, because it's 2 cos, it's going to be minus 2, 2. And this one is going to be minus 3, 3. Now looking at my graph, if that's 1, 2, 3, and that's minus 1, minus, oh, I don't know where I was going with that. Minus 2, minus 3, straight away we figured it out, because this thick black one here, which is f of x, that is starting up at 3, so that will be 3 cos of 2x. This really close together dotted one that ends up here, g of x, that's going to be 2, so that's 2 cos of 3x, and that means that the last one will have to be cos of 3x. Okay, so another way you could look at this is there are 2 that seem to move at the same kind of flow, as in they cross the x-axis at the same points. That means that their period would be the same, and that would have to be these 2 here, because they're both 3x. Okay, so they're both cos of 3x, so they're moving a little bit quicker than the cos of 2x. So remember we said putting a number in front of the x there kind of compressed the whole thing. It made it move through it a little bit quicker. So the period of the function, instead of being 2 pi, so the period, I'll do it in a different color. So the period of both of these is going to be 2 pi over 3. The period of this one is going to be 2 pi over 2, which is pi. So that's how quickly it rotates. So I'm actually going to deal with f of x first. So it starts up at the top, I trace it down, and it ends up the top. So this line here is its full rotation. So that's actually pi. And it goes, so that's 2 pi. So that gets me something quite quickly. How quickly the others rotate, so it starts up here, and I follow it through, and there's its rotation. So that one here is 2 pi over 3. So it's kind of like 2/3. And then there's 4 more boxes till it's pi. So I'm going to divide that into 4 more boxes. And that's pi over 3. And 4 more boxes up from pi. 1, 2, 3, 4. So that's 4 pi over 3. 1, 2, 3, 4. 5 pi over 3. And 2 pi. And we can split it out even further if you want, but that will be sufficient for the question. So let's look at another example here. And this is from the 2014, again a paper 2, and it's question 5, part A. So the diagram below shows the graph of the function f of x equals sine of 2x. So straight away when I see sine of 2x, I know two things. I know the range is going to be minus 1, 1, that's not going to change, and my period is going to be 2 pi divided by 2, so that's pi, that's how quickly it rotates. And I can see that there, look how quickly it rotates. On the same diagram above, sketch g of x is equal to sine of x, and h of x is equal to 3 sine 2 of x. So this one very straightforward, minus 1, 1, and it's going to have a period of 2 pi. So let's do that first. Just try to keep it all. I'm going to do this one in like a blue. So then we'll be able to like see it so it's color coded. Sine means it's going to start at 0, 0. It's going to rotate. It's going to do one full rotation in 2 pi. So basically it's going to move up. Get my pen back. It's going to move up about halfway. So it's going to hit my maximum point here. It's going to cross the x-axis here. 1, 2, 3, 4. It's going to hit its lowest point here, and it's going to come back up here. So you're going to get this idea here, if I can draw properly on the computer. Okay, so that one there in blue is g of x equals sine of x. So the next one I'm going to do, and I'll do this one in green, is 3 sine of 2x. So the first thing I have is, because it's got 3, it's going to go down to negative 3 and up to 3. So that's going to be my min and my max. And the sine of 2x means it's going to have a period of 2 pi divided by 2, so a period of pi. So it's actually going to go through the same points as the original one here. So I'm going to go through these points, but my difference is it's going to move up to be 3. So that maximum point is going to go there, minimum point here, maximum point here, minimum point here, maximum point. So you go up, and it's going to go down. Oh, this needs a little bit. So up to here. Excuse the drawing on this, very hard to draw on the screen, but you can do something a lot better if you're working through this question yourselves in your papers. And up here, and that is h of x equals 3 sine of 2x. So there are my sketches. So now we're going to look at 3 questions, and they're all exam-based questions. From one is from the Educate sample paper, we have one for the GEB mock, and one for the Examcraft mock. The first 2 are a bit more straightforward, because they're section A questions, 25 marks. They're working with solving equations and working with the functions in a bit more straightforward kind of way, but there's some interesting pieces on it, that's why we're covering it. The last question from the Examcraft mock, the 2018 mock, it's a section B question, which means it's a longer style question, and it is showing the application of what we've learned in this video, this idea of solving, the idea of functions, and applying it to a real world scenario, which we're seeing more and more in the papers. So there are 3 very good questions that we're going to work through now. So the first question is, if tan of x is equal to minus a half, please place a tick in the quadrants, the diagram on the right where x could be located. So if we go back to our unit circle, we know in this section the cos is positive. Here all of them are positive. Here sine is positive, and here tan is positive. So the 2 places where tan is then negative is here and here. So without using your calculator, evaluate the tan of 330 degrees. So if we take a look at this diagram that they gave us, 330 would be somewhere in around here. Okay, so there's my 330 degrees. That would leave me with a reference angle here of 30 degrees. So let's go back to blue. So that's 30 degrees. However, it's not just equal to the tan of 30. It's going to be equal to minus the tan of 30 because of which quadrant it's in. So the tan of 30, if we go to page 13, because that's what it's saying, refer to the information on page 13, and basically not using your calculator. So if we go to page 13 and we look up 30 degrees, for tan it gives us 1 over root 3. Perfect. Now, if you were to do that on your calculator, so if you put into your calculator tan of 330, you will get the same answer, but it will look slightly different. So they will be able to tell that you didn't use page 13. If you put it into your calculator, what you get is minus root 3 over 3. Now, that's coming from the fact of minus 1 over 3 has a third in the bottom, and realistically, we should generally not have that happen. So we rationalize it by multiplying above and below by root 3, which gives us the answer from the calculator. Okay, just in case you're double checking your work, but this is using page 13 as requested. So, part B, using the grid below, plot a graph of y is equal to tan of x for x between minus 90 and 270. Use your calculator to work out y to one decimal place. So putting that into the calculator, these are the values we should get. Notice that you won't be able to get a value of the tan of minus 90, the tan of 90, or the tan of 270. So that's really, really important. There is no function at that point. There is no value for y at that point. If we are then to plot it, we should get something that looks like this. I've drawn in the 3 lines where there is a break in the function. This function, the tan of x, is a discontinuous function. It means that you must lift your pen in order to draw it. So it's not a continuous function. You can't just draw it without lifting your pen. It happens at kind of the 90-degree interval and the 270-degree interval, and in rotations after that. So after 270, it will happen again 180 degrees. So we get this kind of shape here, which you should be familiar with. It then asks, is y equal to tan of x a function from minus pi over 2 to pi over 2 all the way into the real numbers? Explain. And just to note that these round brackets here not including. So you're not including here negative pi over 2 or pi over 2. So I suppose there's a few different ways that we can answer this. And what I will be talking about here is the vertical line test for function. Vertical line test. Now, it passes the vertical line test, and what that means is, and you do need to explain it. So a vertical line can be drawn between, between minus pi over 2, which is 90 degrees, minus 90 degrees, and pi over 2, 90 degrees, and it will hit the graph once and only once. Therefore, it is a function. So, tan of x is a function. It is what we would call discontinuous, but it is a function. And in between minus pi over 2 and pi over 2, in that section there, it is continuous, and if I draw a vertical line anywhere, it will hit the graph once, but only once. So it is a function. So next it asks, what is the period and range of this function? So the period of the function is how often it repeats, so that's 180 degrees, or if you want to work in radians, it's pi over 2. And the range, it goes from minus infinity to infinity. Remember, when you're using infinity, we always use the round brackets to show that infinity is not included. So the last part then says, find the solution of tan is equal to minus root 3. So tan of x is equal to minus root 3. So drawing out my unit circle here, I get my C, A, S, T. And where is tan negative? And we kind of already worked with this. It's these two spots here. So the first thing that I'm going to do is I'm going to say, well, let's work instead with the reference angle, tan of A, where that's equal to root 3. And working out, I'm actually going to use page 13, but you can of course use your log tables as well. That gives us 60 degrees. Notice that because they've given us this in degrees, we are working in degrees. So my reference angle is 60 degrees. So I could put that in here. There's my 60 degrees. And there's two other options. Well, there are two options where it's equal to minus root 3. So we have this quadrant here where this piece is equal to 60, and this quadrant here where this piece is equal to 60. So working in the second quadrant and working in the fourth quadrant. So in the second quadrant, my x is going to be 180 degrees minus my reference angle, which is 120 degrees. In the fourth quadrant, it's going to be 360 degrees minus my reference angle, which is 60 degrees, which gives me 300 degrees. And that gives me my two values for x when tan of x is equal to minus root 3. So question 2, find the general solutions that satisfy the equation 2 cos of 3 theta is equal to minus 1, and hence solve the equation in the domain theta is between 0 and 2 pi. So there's a lot going on in this question, so let's start off with what we have. So 2 cos of 3 theta is equal to minus 1. So the cos of 3 theta is equal to minus a half. Now, to ensure we don't do any division before we need to, the easiest thing to do is to let x equal to 3 theta. So instead we're going to look at this as the cos of x is equal to minus 1 over 2. Now, because it's negative, we're going to use instead a reference angle A, which is equal to a half. So now we get that A is actually equal to, using page 13, we get pi over 3. Now that is actually 60 degrees, but they have asked us here clearly to work in radians. Now I've used page 13 to get pi over 3. However, if you want to use your calculator, that's fine. Just make sure it's in radian mode. So now I'm going to go to my unit circle, and I have my C, A, S, and my T. So here are the two places where cos is negative. So my two places where cos are negative is my second quadrant and my third quadrant here. So now I'm going to work through and figure out these two solutions. So coming back, I know that if I have this angle here is pi over 3. I have an angle here that's also pi over 3. And to work it out in the second quadrant, I work with the fact that this is 2 pi, this is pi over 2, this is pi, and this is 3 pi over 2. So my second quadrant is pi minus pi over 3, which is 2 pi over 3. The next one is my third quadrant. And my third quadrant, the angle is here, pi over 3. So this one is pi plus pi over 3, which is 4 pi over 3. So that's my first two values of x. Okay, so that's x and x. So x, I'm going to put it up here, is 2 pi over 3. And x is also equal to 4 pi over 3. Now, if I want to turn that to a general solution, what I would say is 2 pi over 3 plus n times 2 pi. And here x is equal to 4 pi over 3 plus n times 2 pi, where n is an element of 0, 1, 2, blah, 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 all the way up. So that's accounting for all its rotations. And that's my general solution of x. However, they want our general solution of theta. So we have 3 theta is equal to this, 2 pi over 3 plus n 2 pi, and 3 theta is equal to 4 pi over 3 plus n 2 pi. Now, to get the general solution of theta, we're going to divide everything across by 3. So that's 9 plus n 2 pi over 3, and theta is equal to 4 pi over 9 plus n 2 pi over 3. And that is my general solution for theta. Okay. Sorry, no. Try that again. So that's my general solution for theta. Now, they want then specifically the solutions between 0 and 2 pi. So any angle has 2 in the majority of cases, apart from a few exceptions, it has 2 angles between 0 and 2 pi. Because we've now put in a 3 theta, there is now 3 by 2, which is 6 solutions. So let's go with it. Let's first of all look when n is equal to 0. So theta is equal to 2 pi over 9, and theta is equal to 4 pi over 9. When n is equal to 1, theta is equal to 2 pi over 9 plus 2 pi over 3, which would give us 8 pi over 9. Yeah. And here we would have 4 pi over 9 plus 2 pi over 3, which gives me 10 pi over 9. 6, yeah, perfect. And then the last two will come from n equals 2. So theta is equal to 2 pi over 9 plus 2 times 2 pi over 3. And that should give me 14 pi over 9. And the last answer for theta is going to be 4 pi over 9 plus 2 times 2 pi over 3. And that equals to 16 pi over 9. So there are my 6 solutions for theta, which link up between 0 and 2 pi. So the diagram shows 2 points on the graph of the function y is equal to f of x. So we have a few little bits here that I want to mark on my graph. So it's important to see that this is my y-axis and here is my x-axis. That's my 0 point. Now, this has a nice little point on it, so I want to mark that on my x-axis. I don't want to mess up the straight line too much. They've told us here this is pi over 2. And we have another bit here. So notice that pi over 2 can be split into 3 pieces. Okay, so if I have pi over 2 and I divide that by 3, it's the same as pi over 2 multiplied by a third. So that gives me pi over 6. So this first bit here is pi over 6. The next one is 2 pi over 6. However, if I have 2 pi over 6, that actually simplifies to pi over 3. So that gives me pi over 3 here. Okay, so we can see what we're going up in now. So this one here is 2 pi over 3, and this point here, linking down here, is 5 pi over 6. And this one is pi. So we're able to break this up as such. It's very useful if you can put numbers onto your x-axis or values so you can see what's going on. It first of all then says, state whether f of x is a sine or a cosine function. So the first thing we want to look at is where does it cross the y-axis. So on the y-axis, the point that we have is 0, 3. Therefore, it's a cosine function. And the reason is sine will always pass through 0, 0. Okay, so it is a cosine function. It's not just cosine. There's changes to it, and we're going to look at that in the next part. So write down the period and the range. So the easiest one for us to do is the range. So the range is the maximum point to the minimum point there. So if this is 3, every 2 block means 1. So this point here is actually minus 1. So our range goes from minus 1 at the bottom to 3 on the top. And what I'm just going to write here is note it's not symmetrical. And that's going to be really important as we move on to the next question. So this is not symmetrical, so that's a big deal. The next thing we want to look at is the period. So how does it repeat? So it repeats when it's back up here. So it has taken 2 pi over 3 to repeat. So if we take a look, here, that's where it starts. This is where it ends, and that gives me 2 pi over 3. And we're going to use that. So I'm going to use the word normal, but a normal period, when it's just the cos of x, is 2 pi. So therefore, it must be the cos of 3x, and that's important. Okay, so this is cos of 3x. So now it wants us to find the equation of the function. Now, this is just a little bit tricky. We know that I've just said it's going to be the cos of 3x. That's important. However, the actual range is different. So there's definitely a value a here. And because it's not symmetrical, there's a constant that has been added on. So there's been some shift up and down. So effectively, if we wanted it to be symmetrical, we would have to bring the graph down. So by 1 value. So if I brought every value down 1, so every y value is reduced, my range is then reduced to being minus 2 to 2. And that's more like what we need. So effectively what's happened is the actual function itself has been shifted up once. And if you go back and look at your diagram, they've shown us where kind of that horizontal middle line should be, and it's the dotted line. And if you have been marking in your values of y, it appears at 1. So that means our c is 1. So we have cos of 3x. And when we reduce the range because of that plus 1 to minus 2, 2, that will tell us that there's a 2 in front of the cos of 3x. So that's really, really important. If you look through the work solutions, what I've done is I've worked kind of through it logically, I suppose. So if I'm not explaining it, how would you figure it out? Hopefully this all makes sense from the graph. The idea of that plus 1 at the end is just a little bit different. But really what should happen is when you're looking at that range and seeing that it's not symmetrical, you should know, okay, this is going to have some kind of impact. So now we have our f of x, which is equal to 2 cos of 3x plus 1. And we want to find the function where x is equal to 100 pi. So we get 2 cos of 3 times 100 pi plus 1. which is equal to 2 cos of 300 pi plus 1. Now, there's obviously a lot of rotations here. So what we're going to do is we're going to see, well, look, how many rotations are there in 300 pi? So we're going to divide that by 2 pi. So there's 150 rotations. And because 2 pi kind of divides evenly into this, it's actually finished on a rotation. So what we end up with is 2 cos, and this is equivalent to 2 pi plus 1, which is equivalent for cos is the cos of 0 plus 1. Now, the cos of 0 is 1, so we get 2 times 1 plus 1, which works out at 3. You can, of course, use your calculator, and if it's in radian mode, it will work like that, but it's important to be able to reduce the angles, and I'll show you here. So we have 300 pi, and we're going to divide that by 2 pi, so it means there's 150 exact rotations. If we got a decimal there, it would mean there was so many rotations and then some, and it's the and then some that we want to figure out. But here there's just 150 exact. There is no remainder, so we know that actually they're full rotations. Therefore, 300 pi equals to 2 pi, so full rotation, or 0 as well. So remember your unit circle. This point here is equal to 2 pi, but it's also equal to 0. So let's look at our final example. This is a trigonometry exam question. It was from a section B, so it was worth 60 marks in total, and it was a much more practical kind of question than the ones we usually see. So a Ferris wheel has a radius of 22 meters and is boarded from a platform that is 2 meters above the ground. The 6 o'clock position of the Ferris wheel is level with the loading platform for the viewing cars. So a viewing car reaches the highest point of the revolution after 3 minutes. The movement of the wheel can be represented by a sinusoidal function. When this function is graphed, the horizontal axis represents time and the vertical axis represents height of the first viewing car as it continuously moves around. So some things we need to talk about. So first is sinusoidal, this function here. Now, again, remember that this is a mock, but when we talk about a sinusoidal function, it is a curve that describes a smooth periodic oscillation. So just to be really clear and really careful, this could mean sine, which is kind of the obvious one, but it can also mean cos because it's cosine. So either of these are valid here. It wouldn't be tan because tan doesn't have an oscillation as such. It is disjointed, it is discontinuous. So we're talking about either sine or cos. We are asked in part A then, in relation to the graph of the movement, write down the equation of the midway line. So just to have an understanding here of our height. So it starts here and it told us that this is 2 meters above the ground. Its center point here is then where it's turning from. This is 22 meters and then this is 22 meters, both because it's that just represents the radius. So there's my maximum and there's my minimum. So they're just distances for the moment. And if I was to think of these in terms of an actual number line, this here would be 2, this will be 24, and then this one here will be 46. So that gives us a better sense of where we are on the number line as opposed to distances. So it says, in relation to the graph of the movement, write down the equation of the horizontal midway line. So my midway line is going to go through here. And what is that equation? So it's a horizontal line, so the equation is a little bit simpler than ry equals mx plus c. Because it's horizontal, it's actually a constant. So it is a straight line, but it's a constant. It's a constant horizontal line, which means it's going to be in the form y equals and some value, so y equals 24. And really 24 meters, but they couldn't work with you. They couldn't dock you marks for that if we're talking about a function. So that is our midway line. So seemed a lot more difficult than it was. So part B, write down the range of heights a person will experience during one full revolution of the wheel. So this is talking about how high does it go and what's its minimum point. So we saw that the lowest point it is 2 meters above the ground, and then the highest point is 46. That came, and they are both meters, and that came from our diagram on the previous page. So both of those parts are worth 5 marks. So then write down the period of the graph representing the movement of the wheel. So it tells us that it takes 3 minutes to get to the top, which means one full revolution. So one revolution is going to equal to 6 minutes. Okay, so our period is how long it takes for one revolution. So in this case, our period is simply equal to 6 minutes. Again, another 5 marks. So during mathematics class, 2 students are deciding on the type of graph that should be used to represent the movement of the Ferris wheel. Tom thinks the graph is a sine wave, while Joan believes it's a cosine wave. Do you agree with Tom or Joan? So basically, do we think it's sine or cosine? So the best thing to do here is to do some kind of sketch. So here is my Ferris wheel, here is my X and my Y axis. They told me that my Y axis is representing the height and the other is representing time. So when time is 0, we're starting at the bottom and we're moving up, 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 up. So we're starting, here is my starting point. So what I get is something that looks like this. So it starts at 2 and it goes up, down, up, down, up, down. Now, what I would say about this particular question, if we go to the syllabus, it doesn't mention anything about the transformations moving up and down for the sine and cosine rule, or for the sine and cosine functions. It's good to see it, but I don't think this would be something that we would see on the paper. They specifically talk about this compression and the symmetrical movement. But in this case, we're not going through 0, 0. Now, basically, one of the things you would have maybe learnt is the sine graph always starts at 0, 0. Now, that is not necessarily true. It will start at 0, 0 if the x-axis is our center line. Now, here, as we already figured out in part A, our horizontal center line is actually 24. So when we put in that center line, we need to make a decision. Well, if our graph starts at that center line, then it's a sine graph. If it starts at either the top or the bottom, it's going to be some version of a cosine graph. So based on this movement and what we have, this will actually be a cosine graph. And the answer and the logic, I suppose you would say, is that the fact that it doesn't start at that midway line. So remember, sine will always start at the midway line and cosine will always start either above, so at the top, the maximum point, or at the minimum point. So we agree with Joan because we think it's cosine at minimum point. Sine always starts at midway point. Okay, and that was actually worth 10 marks in that exam. So part E says, one of the functions below can be used to represent the motion of the Ferris wheel. Using your answer from A to D, choose the correct function and fill in the values for A, B and C. So we've decided that it's a cosine rule. So the first thing I'm going to do is I'm going to say, well, it's definitely not this one and it's definitely not this one. So that just leaves us 2 to work with. So what I've put in here is how our cosine graph usually looks. So notice here that we usually start in a cosine rule at the maximum point. And in ours, we're starting at its minimum point. That means that it's flipped. That means that there is going to be a negative put in front of our cos in order for it to flip. So we're looking at this one here because of the minus b cos ct. So we have a few things that we need to put in. Now, it really is up to you where you start. For me, I would talk maybe about the shift. So A. So A is its shift. So it has shift up from where? Well, the center or midway line should be 0. And actually, we're shifting it so that it's at 24. So actually, this shift, this A added on at the start, is going to be 24. We want to talk about the amplitude. So actually just this height here. So this height here is 22, and we should have a mirror image down here of 22. For any cos or sine graph, that should be 1. But actually, when I put a constant in front of my sine or my cos, that will stretch out the amplitude. So B here is given by the amplitude, so that's minus 22. And it's going to be cos of something t. So we need to work out that number in front of our t, so ct. So that's the last piece we need to work with, and we're going to, for that, go back to the idea of period. So I'll work here for a second. So remember, our period is equal to 6. So our period is usually 2 pi, but when we have any number put in front, so like that's c, we're going to end up with 2 pi over c. So, oh sorry, that should be c, 2 pi over c. So this equation here, we're going to solve that for c. So for us, that gives us 6 is equal to pi over 3. So this gives us pi over 3t. So that is our function f of t worked through. So we're dealing with a lot of what we've already seen, but putting it together. Just to note as well, like I said, that adding in the a at the start, officially that is not written in the syllabus that's required, but it's good to see it just in case. It's not a hard part to deal with, so if it did come up in a mock, you'll have seen it here. So F is draw a suitable graph to represent the motion of the Ferris wheel for one full revolution starting from the loading platform. So it's going to look something like this. And we had that sketched out before. So remember, our minimum point is where we're starting. That's approximately 2. Our maximum point up here is about 46. Our midway here is 24. So it's probably just in around there. And we can work through it. A full revolution took 6 minutes. So that is our period of our function. So part G, if a person rides the Ferris wheel, what height will they be after 2 minutes? So let's take our function that we worked out in part E. So from part E, we worked out our function f of t is equal to 24 minus 22 cos of pi over 3t. And we are working where t is equal to 2 minutes. So we sub that in. So we're doing f of 2 is 24 minus 22 cos of pi over 3 times 2. And that will give us, when we work it out, 35 meters. That was actually worth 10 marks. Now, bear in mind, if you messed up on E, you picked the wrong function, you have the wrong values, as long as you're doing your substitution here to whatever you had on E, you will have you will get all your marks. So it's really important that even if you think, oh, it's not right, that you keep going with it, because they will only penalize you once for a wrong answer as long as there's no oversimplification.